Okay, folks, so the conclusive part of statics, ladders now. This is all about the diagram, but all you'll see is that statics, whether it's flat beams like you've done at the basics at the start, or whether you've done the hinges and now you're doing ladders, it's just literally resolve and take moments around a pivot point. That's all you got to do. That's the only method it is. Resolve and take moments, okay? It's about knowing where to take the moments about, where make it sensible, and your diagram has to be bang on. Alright, so a uniform rod AB of mass 40 kilos and length 10 meters rests with the end A on a rough horizontal ground. Okay, the rod rests against a smooth peg C, so that's keeping it upright. So basically what we have is, here's our beam, remember nice big diagrams. So this is our point A, it's on the ground, and what's keeping it up? A peg. So notice this is like a cross section. If you imagine this is like a pole sawed across its cross-sectional area, and this is a plank of wood against it. So basically you've got a profile view. That's what we're looking at here, okay? So uniform rod, so we know that means in the middle. It's saying AC is 8 meters. So if this is C, right, notice straight away you're going to have a reaction force at C. This is a normal reaction, remember, because you've got a circle, you've got a beam touching it, so at the point of contact, a normal reaction is going to take place. Whenever something touches a surface, it's going to have a normal reaction to the surface. Let's think about why, because the same thing is going to happen at the floor here. So there's a normal reaction at RA. Think about it, if a ladder was made up of like an infinite number of particles, essentially notice if the particle, you can think about it as circular, as soon as it touches the floor, you can see that the floor becomes a tangent, and then for the normal is straight up, right? So if I have a plank of wood here, here's the tangent to the circle, and the normal is 90 degrees to that tiny point of contact. Do you see? Okay, so uniform rod, remember it's 40 newtons, so 40 kilograms, so there's 40 G, there's 5 meters. It says AC is 8 meters, so that's 3 meters, and that's 2 meters there. Okay, great. And it's in limiting equilibrium, and remember it's rough, right? It has to be, otherwise this thing would slide off the floor. But it does say it could be that the peg was really rough and that was keeping it attached, but it's not. This is smooth, so there's no friction at the peg, but there is friction at the ground here. I really would not recommend putting forces like that in line with the floor. You will forget them. Draw the floor and then draw in a separate color or something, some force. There's your frictional force there. It's got to be opposing it, doesn't it? Because it wants to slide out to the left. So something's got to oppose it. And it wants us to find the coefficient of friction. So this is mu RA across here. Okay, so normal stuff. The first thing I would do is resolve. Resolving is the easiest thing to do. Because we need to find what RC is, we need to find what RA is, and then we can start figuring out all the unknowns. All right? So, resolving up, we've got RA going up, and RC is split into an up and a cross, isn't it? And what's that angle in there? Well, that's your 15. Okay? So, plus, we want it going up, so this is our x here, that's next to 15. So hypotenuse cos 15. And that all equals 40G, so that's good. Going across, right? What is it going across? Well, we've got mu RA, that's going to the right. What else do we have? Nothing apart from the thing opposing it, which is this y element here. So force is RC, and then we've got sine 15 because that's opposite. Y is opposite that 15. Okay? So it looks like we've got simultaneous equations here. The only thing is we've got 3 variables, RA, RC, and mu, but only 2 equations. So where's that third equation going to come from? Correct. It has to be from moments, okay? Where is it sensible to take moments from? A, yes, because you want to knock out the most amount of forces possible. So take the pivot generally where the most amount of forces are attached to it, because their perpendicular distance will be naught. So you just ignore them, okay? So we're going to take moments around A, clockwise and anti-clockwise. So what's our clockwise ones? Well, this 40g down here. Remember, past the pivot, make your right angle. So we've got force, 40g. Here's our distance that we're looking for, d. So hypotenuse is 5. It's next to 15, so it's cos 15. There's that force dealt with. Equals, remember RA and mu RA, don't care about that because there's no perpendicular distance for them. Now we've got our force RC, which is already perpendicular to the pivot, notice. Okay, so it's just literally 8. That is the perpendicular distance. So from here, I can say that RC is 40g times 5 times cos 15 divided by 8. So this is 236.6518274. Just keep it exact for now. And now I need to shove that in to find RA, and then I can find mu, basically. So at the moment, I've got mu from this equation to be RC, which is 236.6518274, times by sine 15, all over RA. So I need to find RA, and to find RA, I need to shove it into this top equation, that RC. Okay, so from here, RA must be 40g, subtract RC cos 15, so 40 times 9.8 minus answer cos 15. So that's 163.411888. So this must be 236.6518274 sine 15. I didn't really need to put all those decimal places in there, but I'm just going for it. So we've got 236.6518274 sine 15 divided by that answer, and we should get 0.375 to free SF. And that makes sense because we know that mu is normally between 0 and 1. If it's above 1, probably something's gone wrong, but it's not impossible. Okay, last example. That's the same slide. Ladders, right. So a ladder AB of mass M and length 3A. So notice, going to get some letters in here now. Has one end A resting on a rough horizontal ground. The other end B rests against a smooth vertical wall. So I'm being quite kind here because the peg's going to be rough sometimes and the wall's going to be rough sometimes. So we've got my ladder A. Here's my wall, right? Mass M and length 3A. And ladders are generally considered, unless they say otherwise, to be uniform. All right. A load of mass 2m is fixed on the ladder at the point C, where AC is A. So I'm going to assume uniform because it hasn't said that it's non-uniform. Here's my floor here. Okay. So straight away we've got a reaction at RA, and we've got a reaction at the wall at B. Sorry. Notice how it is not out here. It is the surface where the normal reaction comes out. So that, if this was the ladder touching the wall, the tangent is the wall. So the normal's got to come out horizontally. Be really careful about that. Such a common mistake. A load of 2m is fixed at AC, which is A. So here's A across, right? So here's our 2mg. So I don't know why I put 3g here. That's mg, isn't it? Yeah, I just read the distance. So it's 3a. So this is half the length. That must be 3 over 2a, and this must be half a. And there you go. That whole thing now makes up 3a. Right, cool. Oh, it does actually say uniform rod. The ladder rests in equilibrium at an angle of 60 degrees. And remember, it's a rough horizontal floor. So find the coefficient of friction. I really recommend that you write mu RA, you write that force underneath, somewhere you're going to see it in a different color. The biggest mistake is people not labeling friction and forgetting friction, okay? So how do we start? Always the same, resolving up and down, resolving left and right, and then we're probably going to need to take moments. So if we resolve up and down, we've got RA going up, and we've got 3mg coming down, this one and this one, okay? Cool, so we know what RA is now, that's done. Resolving left and right, we got mu RA going right, and we got RB going left. So we don't know what RB is, so mu is RB over RA, which we already know is 3mg. So now we have to take moments, don't we? Because we've only got two equations, we've got three unknowns. So I'm going to take moments around A, exactly, because A has the most forces acting on it. Okay, so let's go clockwise and anti-clockwise. So the clockwise forces, my first one, 2mg is my force. I draw it past the pivot, so there's the pivot. So my hypotenuse is A, and the distance I'm looking for is next to 60, so cos 60, plus next force, mg. Here's the distance I'm looking for. Here's the hypotenuse, so careful of your triangles. So 3 over 2a, it's next to 60, so cos 60, right? Equals, so now we're doing our anti-clockwise ones. Here's my force, RB. See how I'm drawing it past the pivot point, right? So I make that right angle there. So this is the distance I'm looking for. So force is RB. Distance is y. How am I going to get that? Well, I can see this is a z angle, so that's 60. Our total length of the ladder is 3a, and 60 is opposite y, so I know I'm straight into sine 60. Okay? So therefore, we can find RB, because RB is going to equal, the a's are all going to cancel, and the mg's are going to stay. So at the moment we've got 2mg cos 60 plus 3 over 2 mg cos 60 all over 3 sine 60. Okay? So if we add that up, we get 2 times 9.8 times cos 60 plus 1.5 9.8 cos 60 divided by 3 sine 60. So 6.601 blah 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 m. Okay? It might be advisable just to stick it directly in, but anyway, that's what we've got. So that's RB. And sorry, we need the G's in there. So mg. No, we don't. No. Let's do that again. I'm going to leave the G in there this time. So 2 cos 60 plus 1.5 cos 60 over 3 sine 60. Okay, so I've got 7 root 13 over 18 times G. I think it's easier to, and M in there as well. It's easier to leave the G in there because it's just going to cancel, isn't it? So 7 root 3 mg over 18. Really careful not to lose that mg. And therefore mu is going to equal RB, which we just found, over 3mg. So the mg's cancel, which is exactly what we wanted. Divide by 3, so 7 root 3 over 54, so 0.225 to 3SF, which again is good because it's between 0 and 1, and that should be okay. Just to recap then, ladders, hinges, beams, resolve first, that's the easiest, then take moments. Remember, if the angle is opposite the force, you're going to use hypotenuse sine. If it's next to, hypotenuse cos. Always draw the force past the pivot point. Make your diagrams really accurate. Get that friction underneath the floor. right? Not on the floor. It always messes up that way. And watch out for your normal reactions, that they are actually 90 degrees to the surface and not 90 degrees to the beam itself, right? It's to the surface the beam is in contact with. Okay.